One common example for the CISO model is SF4 or sulfur tetrafluoride. So as you can see in the white over there, one way you can use to identify if the chemical equation that has been given has a CISO structure is by using the formula AX4E1, with A being the central atom, which in this case is the sulfur as it has the lower electronegativity, X being the number of constituents, has actually 4 constituents over there, and E being the number of lone pairs in the model. As you can see, it also has 1 lone pair in the 3D model. So for the angles of the CISO model, the angle from the both end of the axials, which is here and here, is equivalent to 180 degrees. The angle from the axial to the equatorial, which is over here and here, the model here and also here to here, is equivalent to 90 degrees. And lastly, the angle from the equatorials, from both of the equatorials, as you can see over there, and the 2D and the 3D model from here and here, there, is equivalent to 120 degrees. So as to conclude, a CISA model has at least 5 things surrounding the central atom, with 1, 2, 3, 4, and 5, with 4 of these things being bonded and the other being a lone pair.
Hi there everyone. I'm gonna talk now about the trigonal pyramidal. It is defined as the shape in which 3 chemical bonds are arranged in trigonal manner with one lone pair on the central atom of the molecule. So later I'm gonna give an example, and this will show about how the trigonal pyramidal is formed. Okay, so I'm gonna give an example of ammonia. This is a chemical structure with NH3, 1 N and 3 atoms of H. So we know that N has 5 electrons, 5, and then the H is 1 here. So since it's 3, we're gonna multiply the hydrogen to 3, so it has a result of 3. Then now I'm gonna show to you the structure, the N. Since it is the central atom, let's place it in the middle and let's put the 5. So we connect the H, and another H. Since it's 1, we're gonna make it to be balanced to make it happy. So what we're gonna do is we're gonna share the electrons to each other. So we're gonna connect their line, share, and share. And we have 2 electrons left. So that can be a lone pair. We're gonna transfer it there to make it there, and it's already happy. Okay, so now it reduced the band angle from 109.5 degrees to 107 degrees because it's like a tetrahedral angle, and changed the geometry from tetrahedral to trigonal pyramidal. So it's the trigonal pyramidal is somehow related to the tetrahedral form, and this is the tetrahedral form. From 109.5 degrees, it changes to 107 degrees due to this process. So this is my example, and I hope you're gonna understand it. So now it's 107.0 degrees.
I will show you how a linear model or a linear structure is formed by stating some basic example or common example. So we have here a CO2 molecule. So in a linear model, it has a 180-degree angle. And as you can see in the sketch, the CO2 molecule has been aligned correctly or straightly. And in the linear model, it has a 2 shared electron, one from the right side and one from the left side. So there's a one double bond and one double bond the other side. But double bond, you can count it as one shared electron. So we have 2 shared electron. And in this given, we have no lone pair. And by giving U the valence electron of each atom, and how we come up to this structure. So 4 plus 12 is equal to 16, and 16 is the total valence electron of the molecule carbon dioxide. And that valence electron we subtract by 4, that 4 has been get to the two first bond, and the 12 has been distributed in the two oxygen at the right side and left to form that final structure.
This is a tetrahedral diagram. This is its central atom and it has four substituents. A tetrahedral diagram has four substituents because from the root word tetra, which means four. The bond angles for tetrahedral diagram is 109.5 degrees, the same as in methane, which is CH4. Now I am going to show you a 2D diagram of CH4. So the band angle for this side is 109.5 degrees, 109.5 degrees, 109.5 degrees, and finally 109.5 degrees. So a tetrahedral diagram has four things: 4 shared and 0 lone pair.
A trigonal bipyramidal structure consists of two axial atoms and three equatorial atoms, which is in total of 5 atoms. An example of a trigonal bipyramidal is phosphorus pentachloride or PCl5. So the valence electron of phosphorus is 5, while chlorine is 7. Multiply 7 by 5 because it is a pentachloride, so it is equals to 35. Then draw Louise dot structure with phosphorus as the central atom. Then subtract 35 by 5 because there are 5 pairs already distributed in the phosphorus. So, their difference is 30, which means 15 pairs of valence electrons should be distributed in chlorine. So, the octet is now complete. Now let us draw the molecular geometry wherein this angle shows a 90 degrees angle in the trigonal bipyramidal. So, here we go. There on this. So here is a 90 degrees angle, where in this 3D model it is between the axial, the central atom, and the equatorial atom, or it can be below 90 degrees. Below the 90 degrees angle is another angle of 90 degrees, which can sum it up into 180 degrees angle. So in this other phase of the structure, where the actual atoms were formed as a letter Y, has an angle of 110 degrees, wherein the 3D model is located here. Now let us draw the molecular geometry of a trigonal bipyramidal where it shows a 90 degrees angle. So here is a 90 degrees angle in the drawing, and here in the 3D model it is right here between the equatorial, the axial, and the central atom.
So the next Vsepr model is the T-shape. This molecule is made up of 5 sp3d hybrid orbitals and is considered as polar. 3 orbitals are arranged around the equator of the molecule with bond angles of 180 degrees. 2 orbitals are arranged along the vertical axis at 90 degrees from the equatorial orbitals. The shape of the orbitals is trigonal bipyramidal. The three atoms are arranged around the central atom to form a T-shaped molecule. So, for example, chlorine trifluoride. So, chlorine has 7 molecules, while fluorine has 7 times 3 equals 21. So, all in all, we have 28 molecules. So, to illustrate chlorine trifluoride, we have chlorine as its central atom since it is lower than the fluorine. And since there are 3 fluorine, meaning there are 3 bonded pairs. So 3 times 2 equals 6. We need to subtract that from 28 to get the number of molecules. As you can see, there are 6 molecules surrounding each fluorine. So 6 times 3 equals 18. So 22 minus 18 equals 4, meaning there are 4 left for chlorine. So therefore, there are 2 lone pairs and there are 3 shared. So as you can see in the illustration, the 3 atoms are arranged around the central atom to form a T-shaped molecule.
So here we have a trigonal planar model in 3D form. And now I will be explaining to you why it takes shape in this form. So first, I will give you an example, Bf3, which is boron and 3 fluorine atoms. Firstly, we will need to compute the total valence electrons of Bf3. Boron has a total of 3 valence electrons, while fluorine has a total of 7 valence electrons. But since there are 3 fluorine atoms, we will need to multiply 7 by 3, which is 21. Now, in order to get the total valence electrons, we will need to add the total valence electrons of boron and the total valence electrons of the 3 fluorine atoms, and their sum is 24. In illustrating BF3, boron should be the central atom, and so it is at the center of the illustration. And since there are 3 fluorine atoms, we will be distributing it all around boron, the central atom. And we will be creating a bond between each fluorine atom and the lone boron atom. And since each bond contains and connects 2 electrons, we have a total of 2, 4, 6 excluded electrons, and then these 6 electrons will be subtracted from the total valence electrons, which is 24. So 24 minus 6 is equal to 18. The remaining 18 valence electrons will then be distributed along the external atoms, which are fluorine atoms. So we will be putting dots all around the fluorine atoms surrounding the boron. And as we can see, all the atoms are now stable. Let's have the left fluorine. It has a total of 8 valence electrons, so it is stable. The bottom fluorine has also a total of 8 valence electrons, so it is stable. And finally, the right fluorine atom also has a total of 2, 4, 6, 8 valence electrons, so that is also stable. This is very important because in a model, every atom should be stable. As for boron, you will notice that it only has 2, 4, 6 valence electrons. However, boron is a special atom in a way that it can be stable with only 6 valence electrons. So boron, the central atom, is also stable. As we can observe, the 2D illustration is similar to the 3D model, and the distance between each bond in BF3 is 120 degrees, and as is the case for other trigonal planar examples. And so that is a trigonal planar model.